Okay, I think if everyone is back, we can resume the last session of the day.
Okay, let's resume. Where is my screen share? Okay, so I assume that we can all open the notebook number 6. And if you kind of like, you can open it directly in the Google Colab, as I mentioned, but just run it on CPUs, save your GPUs minutes for the notebook number 7. As you see, I have it open notebook number 7 in the Google Colab. It's just because it runs quick on the GPU, and I will show you how to use GPU if you never used it. And here, are we all good with the notebook number 6? And there was some people were complaining about the error where they didn't have a TensorFlow installed. First of all, in Google Colab, it will be installed by default. And secondly, yes, it will be just kind of installed faster than locally. And we can just run it. So when I run, I get this warning message. But you can ignore it. Very likely you will not get the same message because this is related to the fact that, I'm using the Apple computer and it's have some its own version, and the TensorFlow is suggesting that I need to compile the package locally, but this is too much hassle to do it. So, and I won't do it. Okay, again, I'm acknowledging where I took the notebook. And here what we're going to do, we're going to use the package which is called TensorFlow. There is two big kind of packages which are dealing with the neural networks, is the TensorFlow and the Torch or PyTorch. Which to use, it's absolutely irrelevant. By now they are kind of both are good enough, and you use whatever you like. Essentially, you can check, if you don't like the TensorFlow, you might check the same thing and in the PyTorch, but it really doesn't matter. So, and MNIST is such a standard data set so that it's built in. So, and it's located in the TensorFlow in the following path, under the Keras. Keras was on some stage, a wrapper around TensorFlow, which was simplifying the data science tasks. Dataset MNIST, and you need to load it. And for the first time, when you run it for the first time, it might load it from the internet. So, and what I suggest that you do before kind of running it, so you can see, okay, how the data is looking like in principle. So where all those my 0, 1, 0 is coming from. So if I just try to see, what is the trained data, you see, you get a bunch of arrays, and afterwards you get an array like this. So what are you dealing with? What is the data? So we can try to see, what the data is. And the data is, trained data is a tuple. So tuple means something, which is can be addressed as 0 and 1, yes? So kind of that will be the first element of the tuple. And you see, and this is array. So we can check the dimension of this array. And it's a 60,000 by 28 and 28. So the first index is the index in our training samples. And second and third index is exactly kind of, it's our kind of training samples, is our images 28 by 28. Yes, so we can, if we wanted to see how the one image is looking like, we can do first 0 is related to the first object in the tuple. And now we're going to get an element 0 out of this 60,000. So it's going to be an array 28 by 28. And so that's how it looks like. So it's an array with the numbers from 0 to 255. Why to 255? Because it's for the standard grayscale. 0 means, I think, white, and 255 means black, and everything in between. Okay. So, and if we wanted to know what's happening with the second part of the tuple, we'll see that, it's have a number 5, meaning that if we just plot this as the array 28 by 28, we're going to see the handwritten digit 5, and we're going to see it just now. Okay, so this is a little thing so that you can get a better idea of what are we dealing with. And because we know that we have a tuple, now we can load the trained images and train labels from the trained data. So we can say that A comma space B is equal to tuple, and we get an assignment of the trained images. So this bunch of 60,000 array 60,000 by 28 by 28 will get to trained images, trained labels will get into this variable, and the same with the test data. Okay, and now what we're going to do here. So, and why we need to do whatever we're doing here. So in this notebook, what we're going to do, we're going to train just a standard neural network, not a convolutional neural network. And what we need to do, we need to change our data, because our data is, each our image is 28 by 28, array. But we are going to have, just a vector on the input. And that's why we need to change 28 by 28 squared array into just a string. And that's why we're doing reshape. So dot reshape, we will reshape it into the 60,000 images. But instead of afterwards being 28 by 28, it's going to be one line of 784. And 784 is exactly 28 multiplied by 28. Okay, so this is the first thing which we need to do. And second thing which we need to do, because neural networks need to have a values of the inputs, so that's kind of so that they don't blow it up. So let's make them between 0 and 1. And in order to do so, what we need to do, we need to recast the inputs of our data. So because let me show you again. So this is essentially, you see, the entries are integers. And now we need to turn them into the floats, because we're going to divide them by 255. So that each entry of this vector is from 0 to 1. And we do the same for the test images. Okay, so this is the first thing which we wanted to do. So now, if we wanted to check how our data is looking like, for example, X-train. So first of all, we can check shape. Yes, that's we're getting what we want. And how the first image is looking like. Now it's an array of reals. And you see, instead of being numbers from 0 to 255, we get the numbers from 0 to 1. Okay. So now the next thing which we wanted to do, our train and test data is list of, let's see, what is it? Not X, but Y. Oops. Yes, because it's called train labels, sorry. It's an array, yes, of 60,000 entries, exactly how it's supposed to be. And each entry is corresponding label which number is drawn. Yes, kind of like if I ask 0, it will be 5. So it means that the array number 0 here showing number 5, array number 1 will be number 0, number 3 is number 1, and so on. Yes, digits from 0 to 9. So this is our data set. And what we wanted to do, because we want to train the neural network to be a classifier, which by inputting the handwritten digit, which is hidden in these trained images, and we're going to see just now, kind of here a little bit lower, you see how they're looking like. So that's our images. Okay, so in that case, 0 is, it's for the grayscale map, 0 is black, and the 1 is white. Okay, so that's how they're looking like. So this is our handwritten digits, and we are going to learn how to recognize them. But our target variable, yeah, so it's again, it's a 10 classes from 0 to 9, and we don't know how to kind of like, we don't want to force it to converge to kind of like to the number which is greater than 1. And what is typically done, what we're going to do, we're going to convert all the labels to the categorical variables. Have you been told what are the categorical variables are? Yeah, I don't see a reaction, but okay. So what does it do? So we can check very nicely what does it do here. So we get the first label is 0. Let's now do this, and let's see what will be the Y train with the number 0. It's going to be an array which have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries. And whereas 1 is standing, it's standing on the position of the class. So 0, 1, 2, 3, 4, 5. So what does this kind of conversion to the categorical variable is doing? So if we have a list of classes like class number 0, class number 1, class number 2, class number 3, it allows to encode it as a vector where only in the placeholder of the corresponding class there will be 1, and in all the rest places it will be 0. For example, for the train label 1, Y train 1 is here, yes, so because this is a 0 and it's standing in the 0's position. Let's do something a little bit more random. Okay. 2. So what do we going to get here? In the position 2, so 0, 1, 2, we get 1, and on all the rest, 0.0. So from this point of view, that's how we're going to feed the data. So the output is going to be 10 numbers for our classifier. And what the classifier is going to train for is going to train for to have the 1 on the corresponding point if the input is corresponding matrix, which is drawing the number, for example, 2 in this case. Okay? Are we good with that? Setting it up. Okay? So this is just to check the shapes and that to see that the shapes are fine. Yes, now you see kind of our training images are vectors of 784 entries. Yeah, because it's our kind of vectorized matrices. 60,000 in training set, 10,000 in the test set. Training labels are 60,000 of the 10-dimensional arrays, yes, because they have, and that arrays will have zeros everywhere except 1 on the corresponding class, and the same with the test labels. Good. So, and we can see that, for example, how the train image number 1 is looking like, or we can plot a little bunch of the images. Okay. Okay, so now we're going to build model. So there are several machine learning kind of architectures to build the neural networks, and the simplest one is which we've seen with you, and it's called sequential, which means that, you know, the model is composed of the list of layers which are added one after the other. Because sometimes you can have layers in parallel, or you can have a different branches, but that's already kind of, it's a little bit more tricky. For now, the simplest possible architecture is a sequential. Yes, so that's what we're going to do. We're going to activate the sequential model, and we're going to consider a very simple model. So it's going to have one hidden layer, which is going to have 512 units, activation ReLU, and input shape is 28 by 28 or 784. Okay? So the output layer is, again, dense, means it's a fully connected layer. Output layer is another dense layer with the 10 neurons. Why 10 neurons? Because in our classes there are 10 values. And that's it. So we can print the model summary, and the model summary is that, you know, we have our input. Afterwards, we have our dense layer, which have a 40,000 or 400,000 parameters, and the dense layer with the 5,000 parameters, and we get in total this number of parameters. Okay, so we have our model. Now we need to compile it and train it. So when we compile the model, we set up the list of variables which we are going to use. So first of all, we say that which optimizer to use, which loss to use, and the loss is it's called categorical cross entropy, but essentially it's a loss which is counting how many misclassified in the multi-class case in the multi-class classification are we getting, and the metrics is accuracy. So we do the compile the model, and this we can run locally. It's not too bad. So we are going to train it only for the 10 epochs. So don't train for more than 10 epochs. And we also need to specify the batch size. Otherwise, it will take some, default the batch size, and the validation is going to be used the test. Okay. And we're also recording the history. So now we get training process, and we see that, already accuracy is quite good. Okay, so after our model is trained, we can check test loss and test accuracy. So and this is done by, and you see again, the logic is very similar. So you get model dot, we create a model, we're adding layers, we compile the model, and afterwards we do the fit. And in principle, you can just do X train, Y train, and all of this will be done automatically on some by default setting. And now we do model in scikit-learn, it was predict, and here evaluate. And we can get test accuracy and test loss. So we, even for such a naive model, we're getting a very good accuracy of 98%. So, and now we can give a look, because you see when we're creating model, we call this variable history because after this thing is getting executed, it's going to store some values, which could be of interest for us. So we can get this, and I think this will be a dictionary. So we can check what's that. Yes, and that is a dictionary. So you can give a look which keys the dictionary have, but this dictionary have a keys loss and validation loss. And when we have it, now we can plot the loss and validation loss as a function of number of epochs. We just doing a standard plot. And what are we getting? We could see that, as the number of epochs going from 0 to 10, the training loss is going down, but also validation loss is going down. So it doesn't look too bad, and that it doesn't look that we are overfitting the data, and so it might need even a little bit more training before we start overfitting, and we should stop. Okay. Why do you use the testing set for validation set? Isn't the validation set the small subset for the? Yes, yeah. Because it's just a demonstration. Yes, kind of like in principle, we can separate the validation set and do it separately. And yes, but it's just, just because it's a demonstration. But in principle, yes, you're not supposed to use the test. For that, you're supposed to use to separate from the training data, separate the validation data, and on the test, you're supposed to do only the reporting summary. And what we can do, we can also do the same game with accuracy, and we can plot how the accuracy behaving on the training data and on the test data. Okay, so again, we have our predictions, so we can do the predictions. And now we can also check what's happening. Yes, so we can check that, for example, for index 120, the test image is looking like this, which is clearly 5, and we can check that it's 5, so that it's working, and you can play with that and see. Okay, so that's essentially, yes, and in principle, I agree with the comment that, I should be having a separate validation and test set, and we need to do it, but, We also don't do the cross-validation, which you can also do on top of the neural networks. But this you can take as the thing to do on top of what we already do. Because we have an example of using the cross-validation in other sections. And of course, formally speaking, this needs to be done. But this is just a quick demonstration to you how to build a very quick and simple neural network. And we can use the same column now. Here. Okay. But that's kind of like application of the dense neural networks. And you see that in this case, it works not too bad, but in fact, yes, kind of like if you would take some other more involved graphical data sets, the dense neural networks wouldn't work that well, because what you have, the problem is that you kind of like by turning this image into the vector, by just stacking all the rows or the columns on top of each other, we're losing kind of locality information. And this is not good, but this was example to you just to show how to do the dense neural networks. And in order to do the convolutional neural networks, I suggest that we switch to the Google Colab. And it's essentially the same notebook, but the only difference is that we're not going to reshape it to the 784. We're just going to keep it 28 by 28. And of course, that will affect, and we're going to use some convolutional layers. How do we see the underlying code that we call from TensorFlow and scikit-learn? I'm not sure that I understood the question. How do we know that, this is coming from TensorFlow? Because, when we define the variables, like for example, model, we write, where is the, model is TensorFlow sequential model. I'm not sure, am I answering your question or not, or what? And the same with the scikit-learn. So, kind of when I have a corresponding data set in the scikit-learn, I was loading data set in the scikit-learn, and here I'm loading the data set from the TensorFlow. Is it possible to see the underlying codes implementing the function we call from scikit-learn and TensorFlow? I'm not sure. It depends which functions are you talking about. I mean, these functions are coming from, and everything what we're doing here, I think, is coming from TensorFlow, because we don't load in scikit-learn. So scikit-learn is nowhere in this code, because we haven't loaded that package. And so even if we write something scikit-learnish here, it will give us an error. Can we try index 1800? We can try. I'm not sure what are we going to get. Yes. And I just tried the index 1800, and I'm not sure. This looks like a 6 instead of 4. First of all, it could be a mistake, but it doesn't look like anything. It could be both 4 and 6. So one need to check in the kind of like, yeah, it looks like a 6, but it also could be like a 4 where people forget to add. And again, the predictions are not 100%, so they might be a mistake. So this might be one of the mistakes. So nothing wrong with that. Is the way to check the next argmax value? Yes, of course. We just you just do the predictions index, and that will give you an array, and you can check what is the probability distribution, and you know that they are. So with this probability, it's 0. With this probability, it's 1. With this probability, it's 2, 3, 4. So kind of 4 is 73%, and 6 is only 5%. But the 6 is the next one, yeah? Or not? No, next is the 2. So it's thinking that it's 73% here, 20% here, 5% here. Is the way to tell that the right answer is 6. How do you know that the right answer is 6? I don't know. It looks like it might be 6, but you know, if we wanted to learn it till maximum, you know, we can just we just have done 10 epochs. So we can check this index in the next code because the data set is the same. Is it possible to download this data set and read it in pandas? Yes, you have this data set, this data set is downloaded. You know, when you've done this, and when you have a trained data, you get a data set. But I'm not sure what are you going to have in pandas, because, you know, default shape of this data set is a 3-dimensional it's a 3-dimensional array, this data set, and you know, kind of the data set which we have done by turning the 28 by 28 into the vector, we can load in pandas, but okay, it will be a bunch of numbers. Why do you want to have it in pandas? But you can do it because, you know, it's just an array, and the array you can load in pandas. So I suggest to answer this question, or to check in the next notebook, because the data set is the same, index should be the same, so we can check it. Okay, so let's go into the notebook number 7. It would be, as I mentioned, it would be nice to load it in, or upload it into the Google Colab. And here in the Google Colab, I hope you see it, you can choose the runtime. And what we need to choose, okay, so you have, like, by default, you have a CPU, and you need to choose T4 GPU. And these GPUs are available to you if you pay to Google. But for free, only this one is available, but it's better than nothing. And we just run the notebook, and TensorFlow is installed here. So don't forget that the Google is developing TensorFlow. So they have this own package. Okay, so again, we need to load the data set. Again, here is this little codes which we had before, but we don't have to use them. Okay, we do it because I can probably make it lighter, sorry. We have the same train images, but now we don't need to reshape this 28 by 28 in the one vector, because now we're going to use it at the input as matrices. And we need to add 1 in the end, because it's the way how the TensorFlow is eating up the data. It's not up to the choice. But the thing which we need to do, we need to change the type of data. So we need to also normalize it from being array of integers from 0 to 25, or from array of bytes. We need to move it to the array of reals. Yes, so we change the type from whatever it was to the float, and we divide it by 255, but the dimension we're keeping the same. We're doing the same transfer to the categorical variables, and we can check the dimensions that they're the same, and the remaining 2 bits of the code, okay, before we start to build models, are the same. So kind of like because the data set is the same, so I hope that the index 1800 is on the same spot, so we can check it. Okay, so now we're building our first convolutional model. So how it looks like. So we are doing the, again, sequential model, and first, and it's rather arbitrary. So first we need to add convolutional layers with the kind of 32 output channels, and kernel is 3 by 3. Okay, so kind of like that's how you specify it. Yeah, so kind of like this is the size of the kernel or size of the filter. This is the number of output layers. Activation ReLU, and input shape is 2828 by 1. So next is max pool with the kernel size 2 by 2. But again, this you can play with. You can try the smaller convolutional neural network. You can try the bigger one. So it's up to you. So we can add another layer of, and you see here we don't have a dropout, but one can try to add a dropout to see whether it's working nicely. There is no batch normalization, but okay, the neural network is small enough, but one can add it. We're adding another convolutional layers, which is going to apply to this result of these layers with the 64 output channels, and again, kernel 3 by 3, activation ReLU, max pool, and we're doing it again by whatever the design choice. But you can do it smaller, you can do it larger, and you can design by yourself. Okay, so what's happening here? So after we add in one more convolutional layer, now we want to push it to these dense layers because we need to bring it to the answer. So what we need to do, because here what we'll have, our layer structures will be kind of like a rectangular, kind of the 3-dimensional rectangular of the neurons. And now we need to push them into the dense neural network or to the dense layer. So what we need to do, we need to take this shape and reshape it into the just, a string of neurons. And this is done by adding flattened layer, so that this layer, what does it do? It just will reshape this 3-dimensional shape into the 1-dimensional array. And we can add, one dense layer, for example, with 64 neurons and the ReLU activation. And afterwards, we go into the output, which is a dense layer with 10 neurons, where we're going to measure. And the activation is, of course, is a softmax, because here we're supposed to read out our probabilities. And this is much larger network, as you can guess, than in our previous example. So it's probably overkill, but why not? We are running it on GPU. No, in fact, it's not that large, not that many parameters. It's less parameters. It's 100,000 parameters, roughly speaking. But, one can play with architecture, and I recommend that you do it. So you can add the dropout layers, or you can add the batch normalization and things like that. So again, this bit is the same. So we need to add optimizer, which is Adam, and you can also play with other optimizers. Losses, categorical cross entropy, and the metrics is accuracy. And again, absolutely the same thing. 10 epochs, batch size 128. In that example, it was 256. But we can try both, and we can train. And because I'm training on GPU, it's going to be quite fast. Because when I was doing it locally on my laptop, it was taken longer. So it's take here 8 seconds, and here's 2 seconds per epoch. It was taken probably around a minute. Okay, so it's done. And we can, all the rest is essentially the same. But now we have an interesting question about the index. So we can evaluate the model, save the metric, and plot the, and you see, here it looks like that we are already overfitting, yeah? So because our training loss is going down, and the test loss, I think it's going down, and afterwards it starts to going up. So it looks like that we're a little bit overfitting, and so we could probably stop at the epoch 8, which will be here, or epoch 9. And so we can do the same with the training and test accuracy. We can do the predictions, and now we can play with the index. Okay, let's do the 128 first. Yes, and of course it's 8, yes, and now let's do 1800. And let's see what it is. Yeah, you see it's 6. So it was probably 6, and you see that by changing architecture, we can achieve a better result where there is a little bit more local information. Can someone post the modified code for the, why do you need the modified code for something? Sorry, modified code in which sense? Or have you changed it and you need the old version of what? I haven't made any changes. It's in the 6 notebook, and the changes, which changes are you talking about? No, I haven't done any changes. Where it is? Oops. No, there is no changes. This is this dense model. Okay, yes, just go to the code number 7, because this thing wouldn't work by default in number 7 because your data size is different. Because here our data on the input, we really input an array like this. So that here we really input shape is not a vector, but it's a matrix 28 by 28. And that's why, you know, even with a smaller number of parameters, the algorithm is working better because it's have the locality information. It doesn't just treat it as a vector of the numbers. It's have, you know, kind of like features, what is special about 6, what is special about 4 is encoded. So I encourage you to play with this part of the code. Try to add the dropout layers, try to add the Bayesian normalization. You can reduce the number of convolutional layers or increase the number of convolutional layers and see how it's help or don't help. You can change the activation types. So you can go to the good old sigmoid and see that, or tanh, and see does it make things better or worse. In this case, I assume it will make it worse. And you can give a look into the, you know, TensorFlow Keras layers. And you can get the list of all layers which are supported by TensorFlow. Oops. Okay, yes. Here's your convolutional layers. There is a 3D convolutional layers, you know, if you input in the 3D information, convolutional LSTM layers and so on. So you see that there is a huge list of layers which one have, but including, for example, you know, dropout layer and things like this. But as you see, kind of like the amount of layers which are now supported to build the various models is huge. So yes, learn and use it because it's a very powerful tool. Is there a rule of thumb on the number of neurons to use? For instance, if my data is made of Small's representation of molecular graph. I'm not sure. I don't know what is a Small's representation of molecular graphs. And I don't know what does it mean benzene is equal to C1, CCC, C1. I'm not, sorry, I'm not a chemist. Does the dense layer after flattening have to be the same as the previous conv layer? No, of course not. Well, yeah. Because you see, it's not the same because after flatten, you get here 576 neurons because it's a 64 output channels, but you get also here, it's a 64 output of 3x3s. So it's just, you know, I don't know, just for the conversion. So you can have it 32 or you can have it 120. And I think it will work roughly the same. Okay. But Adishina, I really not sure that I understand the question because yes, I'm not a computational chemist and not any chemist by any stretch of imagination. So what I know, what the people are doing using the convolutional neural networks, but in the 3D. So when they try to, for example, encode, because like, you know, your molecule have a position of the atoms in the space, and this is a 3D thing. So in this case, you can use a convolution of 3D layers in order to, not 2D, but the 3D in order to, I don't know, to do some to do some machine learning task, which might be used, I don't know, for some function detection and things like that. Okay. Any other questions? Okay, so, and after you've done your Google Colab thing, what you can always do, if you need to work on the other document, you can go do the disconnect and delete the runtime. And in this case, you can start another Google Doc where you can run stuff using the GPU, because if you don't have a Google Colab subscription, you're not allowed to run several GPU documents simultaneously. Okay, so I recommend that you guys go through the old notebooks, play with them, try to make them work better. And yeah. So this is just, you know, a very brief and yes, maybe a little bit confusing introduction, but at least now you can get an idea, at least those of you. Okay, additional, yes, bring in your question, but, you know, people can get an idea that, you know, it's a huge world. And you need to spend some time in order to understand it and learn how to use it. Is 32 an arbitrary number in the first layer? In the first layer of You mean here? Yes. Yes, this is the arbitrary number, essentially, because this is just the number of output channels, and you can decide how many channels you like. But usually for the computational purposes, I think people take the powers of 2 as this number. And the idea is really that you wanted to grow your convolutional neural networks by adding multiple filters, because what does it do? We're adding filters which are going to be optimized by the training process, and you want them to be relatively large number, because in this case, some filters, if you do things correctly, might help you to do the right thing. But in order to see how it works, just remove a couple of convolutional layers from this network, replace 32 by 16, and see how it's working. And in the previous question, you were asking about the rule of thumb, but you say, for instance, my data is made. It's not that important what your data is made of. How more important is how many instances do you have? So how many data points you have? If you have 1,000 data points, 10,000 data points, 1,000,000 data points, and so on. Okay. To Ilya, I think we're good to go.
All right. Again, thank you, Prof, for the session today, and thank you, everyone. I will upload today's recording once it's available. And again, Prof, this was the last session, right?
Yes.
Yes. So thank you very much. And for the attendees, if you want the notes, they are available on Canvas, and also the recordings will also be available on Canvas and also on the NITheCS YouTube page in case you want to go back. Otherwise, thank you. See you again tomorrow morning, bright and early. Thank you.
Thank you.